Welcome, everyone, to another session of our Data Science and Statistics webinar series. And today we have the great pleasure and honor of welcoming Karen Kafadar. Karen joins us from the University of Virginia in Charlottesville in the United States, where she is Commonwealth Professor and former Chair of Statistics at the University of Virginia. Her research focuses on statistical methods and data analysis in many applied fields like physical, chemical, biological, or engineering sciences. She has received her Bachelor of Science and Master of Science from Stanford and a PhD from Princeton. And previously, she held positions at the NIST, Hewlett-Packard, National Cancer Institute, University of Colorado, Denver, and Indiana University. Karen has also co-authored several reports for the National Academy of Sciences of the United States, including about strengthening forensic science and the anthrax investigation that we all heard about. A recent work concerns statistical methodology for randomized cancer screening trials and classification and estimating error rates in forensic science. Which is one of her important fields of research. She is former editor of JASA Reviews, of Technometrics, the Annals of Applied Statistics. She has been in 2012 president of the International Association for Statistical Computing, an association of the International Statistical Institute, and later in 2019 she has been president of the American Statistical Association. Today, Karen is talking to us about estimating error rates in binary decisions with inconclusive outcomes. Karen, thank you so much for having accepted our invitation to give us a talk in our webinar series. It's, of course, an honor and a great, great pleasure. Thank you so much.
Thank you, Paula. It's really, for me, it's an honor to be able to give this seminar at Porto, which I'm very much looking forward to seeing at Paula's invitation after the Lisbon meeting. And I'll just tell if there are any students that ultimately end up listening to this, I never thought I was going to do anything professionally. I thought the master's degree was the end of the line. So sometimes you don't know. Sometimes you end up with an exciting career like statistics, and I really have enjoyed it. And it's enabled me to meet people from all over the world, like Paula, and had the pleasure of meeting her brother at the ISI meeting in Ottawa. None of that would have ever happened had I not pursued a career in statistics. So thank you for coming. This problem, as Paula intimated, comes about from something that arose in connection with forensic science. And I'm going to tell you about the problem and some indication of where it arises in other situations. Sydney Campbell is my PhD student, and Jordan Radu is a fellow faculty member in the Department of Statistics here. And so the Center for Statistical Applications and Forensic Evidence is a NIST-funded center of excellence. And the federal government every now and then puts out requests for proposals for these centers of excellence, and they're usually fairly long-term and fairly broad. This one was funded in 2015. The head institution is Iowa State with Alicia Karakari, apologies for her misspelling of her first name. University of California, Irvine, Hal Stern. Boy, I got lots of typos myself. And initially Carnegie Mellon, who is Steve Feinberg, he was really the brains behind it. Upon his passing, now the co-PI at CMU is Robin Mejia. We've added two others since then, Keith Morris from the Criminal Justice Department and Brandon Garrett, who's in the law school at Duke. So here's the motivation for this problem. And the question is, how accurate are forensic examination processes? So here's the scenario. Given the evidence from a crime scene, you have a potential suspect. Either the crime evidence actually did come from that potential suspect. They were truly from the same source. We'll call that TM for true match, or they're truly from different sources. Okay. Now, only the recording angel knows for sure. The examiner then conducts an examination and tries to decide, based on that examination, whether it's an identification, which is the correct answer if it is a true match, but it's a wrongful conviction, very bad, if the true situation that the recording angel knows about is actually a non-match. It's an exclusion, which is the right answer if it's scenario B, but you've just freed a perpetrator to go on and commit more crimes if it's A. But the examiner can also make a third assessment. That's called inconclusive, which I'm calling sort of cavalierly, don't know. Okay, they're basically saying, I don't know. Now, if two answers were possible, then calculating error rates would be straightforward. But what if there are three answers? So the true state of affairs is either A or B. The examiner can either say it's an identification or exclusion or an inconclusive. Now, if A is the true situation, that inconclusive decision may be closer to wrong than closer to right. So the guilty person you've just let the guilty person go free to commit more crimes. If the examiner says inconclusive under scenario B, that may be actually closer to the right answer. So the question is, how do we account for inconclusives? So we're going to see if there are big differences in the reported error rates depending on how inconclusive decisions are counted. I'm going to talk about what has been done in the literature previously, and then propose an approach based on level of difficulty. You'll see what I mean by that, and then how we might go about implementing it. So here's the problem in latent print studies. This paper came out in 2011 in the prestigious Proceeding of the National Academy of Sciences. And the data that I'm reporting here is kind of buried in the appendix that you have to download separately. This paper has been, I guess, regarded as the definitive word on how incredibly accurate forensic latent print examiners are. And a latent print examiner, basically, in the crime scene, they lift a print off a glass or a table or a chair or a doorknob or whatever. And then the latent print examiner goes and, studies the print and marks various aspects of the print and then tries to decide if it matches one that pops up in an automated fingerprint identification system. So what Ullery et al. Did is they actually invited examiners to come down to the FBI lab. And these FBI lab had prepared 744 pairs of prints. Okay. In 11, they then presented these pairs 17,000 times. 11,578 of them were actually true matches, and 5,500 were not matches. Okay, and 169 examiners came and they did that, and that was the total. Okay, of those, so of those 11,000 true matches, about 30% of them were deemed by the examiners to be of no value. About 558 of them, of the true non-matches, were deemed of no value, about 10%. So when they went to report the false positive rate, they said only 6 of the true non-matches were reported as matches. So you see that they included in the denominator those 558 that were deemed of no value. But it goes on, the false negative rate, likewise, they included all those of not of any value, those 3,389. And they said 611 of them were declared free, they didn't match, whereas in fact they did. So now if you excluded those deemed of no value, then those error rates go up slightly for the false positive rate and slightly for the false negative rate. But the real problem is that they concluded 3,875 of their 8189 true matches as inconclusive. Okay, that's been getting pretty close to half, and about a fifth of the truly non-matches were deemed inconclusive. So the question is, should we count inconclusive decisions as correct? Clearly there was an answer, either true match or false match. So why does it matter? Well, suppose both Paul and I are given 200 tests, okay? Unbeknownst to us, 100 of them are true matches and 100 of them are non-matches, okay? And suppose we're allowed to say either it's a match or it's a non-match or it's inconclusive, okay? And so Paula is no nonsense, okay? She makes decisions. She doesn't just sit there and be wishy-washy. She makes decisions. Of those 100 true matches, she correctly identifies 80 of them as true matches. She falsely gets 20, she declares 20 of them as non-matches. So the false negative rate for Paula in that case is 20%. Among the 100 non-matches, she correctly gets 70 of them as non-matches, but she says 30 of them are also matches, and that was wrong. So her false positive rate is 30%. Total number of errors is 20 plus 30, or 25%. Okay. Now look at me. I'm wishy-washy. Okay. I'm tentative. I go, well, I'm not really sure. So I declare of those 100, 60 of them correct, but on the others, I'm wishy-washy and I say inconclusive. My false negative rate is 0. Even though Paula got more of those true matches correct, 80 versus 60, she has a higher false negative rate. Likewise, for the non-matches, I'm again wishy-washy. I get 60 of them correct. 40 of them I say don't know. And so my false positive rate is 0. Now, there's just something a little funny about that. Okay, this is not an academic problem. I'm going to describe the differences with the Ullery data. And by the way, this is not limited to just fingerprints. It happens in cartridge case comparisons, handwriting analysis, almost any forensic discipline. In the Baldwin study about 10 years ago, in comparing cartridge cases, they declared 746 of them were inconclusive, and they claimed about 1% error rate. But if you actually counted those inconclusives as incorrect, it actually goes up to 23%. Okay, so remember, Ullery et al. Declared their false positive rate to be 0.1% and their false negative rate to be 5%. And remember, they included the 33, about the 3,400 true matches and the 550 non-matches in the denominator. Okay, so what if you actually took those out, then, and you counted them, the inconclusives, decisions as correct? False positive rate goes up a little bit and the false negative rate does too. But what if you don't include them at all? You just completely ignore them. You pretend they didn't even exist, okay? Even then, which wouldn't be quite right, the false negative rate doubles. But what if you said, well, we're going to count them, but they were correct. You didn't come up with the right answer. Now you can see a big, big difference. Almost a 20% error rate in the false positive rate and a 55% error rate in the false negative rate. Now there was another study, it's actually just an NIJ report, but this one, even though it's small, I think they were honest. So they had 109 participants, they had 80 pairs, and each participant saw 20 prints, 10 that were true matches and 10 that were non-matches. My understanding is that the 109 participants did not know the split. Of the roughly 6,000 assessments, they admit to having excluded 1411 as no value. So about 3,000 mates and about 1,400 non-mates. I'm just quoting there because somehow they lost 16, I don't know where. But they did report the false positive and false negative rates, both with and without counting inclusives. So, and they put this table in, okay? False positive rate, if you count them as correct, was 3%, false negative rate, 7.5%. If you ignore them completely, they go up slightly, but if you count them, but as incorrect, then you see there's huge increase in false positive and false negative rates. Now, Pacheco et al. Also did something else. They gave some idea about the level of difficulty. So they noted that in their 80 pairs, that roughly a quarter of them were deemed by other examiners to be insufficient to difficult. About of the remaining 75%, half were deemed difficult to moderate in terms of their ability to, the clarity of the print, and about half of the remainder were moderate to easy. So in their split, they tried to mimic those same proportions. Okay. So what are the lessons from these examples? Treatment of inconclusive decisions greatly influences reported error rates. Inconclusives occur in studies of accuracy and forensic decisions in many forensic disciplines: latent prints, ballistics, hair analyses, any kind of trace evidence, almost anything. We do need a consistent treatment of inconclusive decisions when calculating error rates, so that we have some sense, the judge has some sense as to whether, say, latent print examinations are more accurate than, say, bite marks, okay? And they actually have bite marks too. They'll look at somebody's wrist and say, oh, somebody bit you here. And they go, oh, that looks like Pedro's mouth. Let's get some impressions from Pedro. So all kinds of questions come up with that. Now, the assays of accuracy do occur in proficiency tests for diagnostic imaging. They also report inconclusives, and frankly, most of them say we don't really know what to do. And in real life, it doesn't really matter that much, because if an image is not clear, if you have an unclear X-ray, first of all, the lab tech actually looks at the X-ray at the time he or she takes it, and says, sorry, we're going to have to retake that if in the lab tech's view it's not clear. But if it gets to the doctor and the doctor isn't sure, the doctor is just going to send the patient back to the lab and say, do another image. So inconclusive decisions there may be less common or troublesome. That's not going to happen in forensic analysis, because once the crime scene police folks leave the scene of the crime, there's no going back to get the evidence. There's really no standard guidelines on when to report inconclusives. There are some recommendations. Mostly labs just have their own policies. Now, there was this very critical report from the National Research Council in 2009. And Paula mentioned this in their introduction. And they simply report. Now, their new identification or certainly can be reached. The result of the comparison is called inconclusive. This report was quite remarkable. Certainly, I don't think anybody expected it would be the blockbuster that it turned out to be. The committee was co-chaired by the Honorable Harry Edwards, and also biostatistician professor at Brown, Konstantin Gatsonis. And just to give you an idea of the issues involved in forensic science, this is probably the most common quotation from that report. With the exception of nuclear DNA analysis, however, no forensic method has been rigorously shown to have the capacity to consistently, with high degree of certainty, demonstrate connection between evidence, for example, latent print, and a specific individual or source. You can imagine that was quite a blockbuster line for the forensic scientists who've been claiming they've been able to do these kinds of matches, identifications. Sometimes they've said with no errors at all, which as statisticians, we know that's simply not plausible. The Organization of Scientific Area Committees, which was a group of the forensic science disciplines, folks who in those different disciplines, they do provide a quality scale to help examiners evaluate prints at the initial stage of a latent fingerprint ID process. So far as I know, it's only for latent fingerprints. But if we did have more information on level of difficulty, that most examiners see when they get a latent print from a table or a glass or a doorknob, that would facilitate more easier comparisons. So let me tell you about what they do currently. There's sort of three views on inconclusives in forensic exams. So ETL Drawer and Nick Skurch a couple of years ago, here's what they said. They said inconclusive can be a correct decision, and if so, then report the error rate in the usual way. Well, I don't know how you know if inconclusive is the correct decision. And so Drawer and Skurch say, ask experts, take majority vote. Well, this is like crowdsourcing, okay? We kind of don't think that crowdsourcing is the way to decide. We already have seen that it's not always people who can make the correct decision. Heike Hoffman, Alicia Carrion, Susan Vanderplas in Law, Probability, and Risk do not offer an opinion on inconclusives as correct or incorrect. They report error rates when inconclusives are counted as correct, count them as incorrect, and count them as ignored. One of the issues comes up is if you're on a jury, what are you going to do with 3 error rates? Frankly, the layperson has trouble understanding even one. So what would happen in real life? My suspicion, there'd be the temptation to choose the rate of most convenience. So the prosecution is going to cite the lowest of those 3 error rates, and the defense is going to cite the highest of those error rates. And then Arcus and Kohler, again in Law, Probability, and Risk, they say inconclusives are not always correct, nor always incorrect. That's true. But then they say, so ignore them. Well, I don't think that's a good idea. That's like treating them as if they don't exist. And as we've already seen, there's a big range in the percent of inconclusives. There are overall over a third of them in the Ullery paper, and even in the Pacheco report, about a quarter of them. Again, as they say, diagnostic imaging proficiency test faces a similar issue, but it really doesn't cause a problem in real life. We can't retake forensic evidence. So here's a really simple idea, and I'd be delighted to hear if other people have other ideas about how to do this. When might an examiner report inconclusive? Well, if it's forensic evidence, often it's subjective. It's based on examiner's expertise, but presumably the probability of an inconclusive will depend on how clear the image is. There's a high probability of saying inconclusive if it's a lousy image, and there's a low probability if it's a very, very clear image. It could also depend on an examiner's risk level. Like we said, Paula will make decisions, and I sit there and I'm wishy-washy. So it could depend on examiner's risk level, with a higher probability if the examiner is more risk averse, like me, and a lower probability if the examiner makes decisions. Okay, even when the image is similar for both people. So studies will differ in their proportions of good and poor quality evidence. As I say, there is a best practices document that suggests examiners can assess print quality using a 6-point scale. So we know about this. We're statisticians. We know how to standardize rates when data can be stratified into categories having different proportions of an important factor. So we know about Simpson's paradox, where we get misleading conclusions that can arise when we collapse data over a relevant category. And in this case, it's quality. So what do we, analogously with reporting incidence and mortality rates of disease, we standardize those rates by the proportions of the standard population in 5-year age groups, so that we don't look at Florida and say, oh my gosh, those people are dropping off like flies because there are a lot of old people living in Florida, versus Boulder, Colorado. We say, gee, I'm moving to Boulder, Colorado because nobody seems to be dying there. Well, that's because there are a lot of young people. We standardize the incidence and mortality rates by the standard population. So now we put them on an equal footing. It's almost impossible to assess examiner's risk level. I don't know how we would do that, but it could be a study that maybe examines how often you make potential participants make decisions. But we can objectively measure latent print quality. And there's a link to the CSAFE website, the Center of Excellence website. It has several quality metric algorithms. So what would standardization do? It would facilitate the comparison of reported error rates across studies within a discipline. It will treat inconclusive decisions consistently across all studies, allowing us to assess whether, say, a judge feels that latent print exams are more accurate, less prone to error than, say, ballistics or handwriting or bite marks. It does require knowing the proportions of a standard population that fall into categories of the relevant variable, in this case, quality. So we'd have to define a standard distribution of OSAC quality levels. Now, Pacheco, in that NIJ report, they give us a good start. Remember, they had roughly 25% were deemed insufficient to difficult. They have only three categories. Half of the remainder were difficult to moderate, and the other half was moderate to easy. But there is a NIST database, NIST 302A, that would be possible to enable the translation of the quality metric score, maybe on a 0 to 100, that's already on a 0 to 100 scale, to a 6-point OSAC scale. And then we could figure out the proportion of the prints that have quality metric 0, 1, 2, 3, 4, and 5, 5 being excellent, and the typical proportion of inconclusive decisions in those different levels. So let's just illustrate what happens, we know, with Simpson's paradox. If we treated inconclusives as errors, okay, so suppose that in study 1, we had 900, one lab had 900 really lousy prints and 100 really fine prints. We had only 2 levels of quality. And we looked at the number correct and in each of those categories and the numbers that were incorrect. And we count inconclusive and incorrect both as incorrect. We had 357 errors out of 900 in the low category and 3 out of 100 errors in the high quality category. And so we have a total of 36%. Whereas with study 2, they had it easy. They had only 200 lousy prints and 800 really high quality prints. So not surprisingly, their error rate looks pretty good. At least it's lower. It's 30%. So if the inconclusives are treated as correct, then study 1 and study 2 have 5.8% and 18% overall error rates. So actually study 2 looks worse. If inconclusive is ignored, again, study 2 looks worse. But again, study 1 had more inconclusives on the hard cases, but fewer inconclusives on the easy cases. So if we want to put these studies on an equal footing, let's suppose that we had a 50-50 split in both labs in high and low quality prints. So if we did that, then study 1 has a 40% error rate and study 2 has a 50% error rate, and those are the standard errors. Okay, come back. Let's see here. There we go. Okay, so again, we could treat inconclusives as correct, incorrect, or ignored, but maybe we want to do something in between. Let's say they're half incorrect if it's low quality. After all, it's not really your fault if you messed up because it was a lousy image in the first place. And counted is completely incorrect if, in fact, you probably should have been able to get it because it was a high quality print. So don't penalize entirely if lousy quality. Well, maybe you could actually do something a little more sophisticated. And if it's lousy quality, really lousy quality, give the weight the accuracy is a 1. Where weight an incorrect decision as a 1, whereas if it's really great quality, then we're going to weight that incorrect. We're going to weight the decision as a 0 because they should have gotten it right. Okay, so what if we did that and we counted half of all the inconclusives in the low categories as incorrect and all of the inconclusives in the high quality categories as incorrect? And again, use a standard population distribution, 50-50. Now we see that study 1 has an error rate of 13% and study 2 has an error rate of 32%. So it does sound like there's a problem with the lab with study 2. Okay, how would we proceed? Well, standardization will require a reasonable assessment of proportions of inconclusives by quality category. When we do this with health statistics, we usually take the whole population as our standard population distribution. And then we look at the proportion of folks in the lower age groups, proportion of folks in the middle age groups, and so forth. Presumably, the probability of an inconclusive, depending on quality level J, will decrease as J increases. So higher quality would mean fewer inconclusives. So you'd have lots more inconclusives if you had low quality, but you'd have fewer inconclusives if you had high quality. The standard distribution will penalize labs for deciding inconclusive out of an abundance of caution. By the way, these studies are not blind. Nothing in forensic science is blind, much less double blind, and they insist that that's simply not possible. By the way, so did the medical doctors insist that blind, much less double blind studies would not be possible in the 50s and maybe into the 60s. And today, I don't think anybody would trust the vaccine if it hadn't been based on double blind studies. So Houston Forensic Science Center is willing to help us in so far as they've got a whole bunch of prints and they know what proportions of them and what quality levels they are that would lead to inconclusive decisions. But we obviously will need others. So this is hopefully we've allowed plenty of time for conclusions. Standardization does allow consistent treatment of inconclusive decisions when estimating error rates. I think that probably the inconclusive does likely depend on latent print quality. It would allow honest comparisons of error rates across studies within a discipline as well as across disciplines. As I say, it would allow a judge to be able to assess whether error rates for latent prints really are less than error rates for bite marks. I think it applies to other scientific disciplines where inconclusive is an acceptable answer. And someone told me that this happens in AI and machine learning, but they don't call them inconclusives. And maybe somebody present here today will know, because I can't remember now what they said, but they said that this situation arises when an algorithm doesn't make a determination, but they call it something else. By the way, changing forensic culture has not been easy. It's really, really tough. I think the Netherlands Forensic Institute, they apparently have had pretty good success with scientists working with forensics, with the forensics examiners, but I think they are unusual. And here are some references. And I think I'm done, Paul.
Thank